And I think we are ready to start. My name is Anechoic. I'm the CEO of Antennex. And with me is Paul Jackson from ElectroRent. And ElectroRent is co-hosting this webinar. First, ElectroRent is going to explain a little bit about who they are, just 3 slides very quickly. And then we are going to start with the webinar. So I would like to give the word now to Paul.
Thank you, Anouk. It's a pleasure to be here in this webinar here today. As said, I'm Paul Jackson. I am the RF applications engineer here at ElectroRent. And ElectroRent's been in business for 60 years, and we're the largest testing and for test and measurement equipment for both testing technology services providing throughout the world. We maintain over $1 billion of inventory, comprising of more than 95,000 units and over 200 manufacturers. ElectroRent offers over 11,000 product types and 7,000 models plus, and continuing to grow. And what does this scale mean for you? It means an access to an extensive selection of test solutions to support your specific requirements. With 20 locations and the ability to deliver to more than 100 countries, ElectroRent serves as a single source for both rental and purchase of test equipment and asset optimization services as well. And as you know, ElectroRent is the exclusive U.S. Distribution partner and solution partner for Antennex, and we're happy to help out in any way we can. Thank you.
Great. Thank you so much, Paul, for that background. I already introduced myself briefly, and I will be introducing more about Antennex and our technology also in a little bit. It's also good to mention that Paul is also your local support in the US if you are from there. Just to briefly go over the content. Sorry, is this working? Can you see the slides? Just give me 1 second. I think I should click on stop presentation, start. There we go. Okay, sorry for that little hiccup over there. A little bit of the content about today's webinar. It's going to be about a 30-minute presentation, so approximately 30 slides, so you can keep track of where we are. I'm going to give you some background on unwanted emissions and measurement techniques for them, some limitations of the current technologies, and how reverberation chambers can be a solution to those. Of course, I will also explain the technology and give a couple of examples that we've tested in the field of actual DUTs, devices under test. And then I'll also go very briefly over some other applications that may be relevant to the audience here. And there will be quite some time for questions as well. So I would like to start with a little bit of a definition issue. I copied these from a recommendation from the ITU, but I've seen these definitions used in various ways. So just to set the context a little bit, spurious emissions are in that recommendation defined as, well, this very long sentence, but basically anything that occurs out of the band, like harmonics, parasitics, intermodulation products, and things like that, that doesn't really impact the quality of the signal. Really out of band. Then there is also the definition of out of band emissions, which was recommended, where it's again out of band, but it is emissions that result from the modulation process. So they're all both very close. They're also used in a sort of intertwined way, and I think that's also fine. But I just want to set the context here of how we're going to use these definitions and what assumptions we have in using them. Unwanted emissions was used in that recommendation as a combination of spurious and out-of-band emissions. But then also I would like to add to that list in-band emissions, which are many things like in nonlinearities, which can also occur in and out of band. In terms of emissions, things like the clock can happen in band, things like noise. So I am right now basically using the larger term of unwanted emissions as basically anything that is happening, nonlinearities, noise, that is either outside of the band or inside of the band, whether or not it's directly impeding the signal. And why is that important, and why are they unwanted, and why do they happen? Well, if you're already working with those on a daily basis, you should already have probably a very good idea of them. But just to make a little bit of a list here, because there is a little bit of nuance again between EMC applications and integrated antenna applications. Of course, the bottom point compliance is something that we look at a lot when we are talking about unwanted emissions. Like, we have to comply to certain EMC standards, both in the aerospace defense area, but also in just general electronics and things like that. So we need to adhere to a certain level of unwanted emissions. We should be lower than that. However, when we are looking at especially aerospace and defense applications and complex integrated antenna systems, we also see that performance is a very large reason why we care about unwanted emissions. So first of all, we have a lot of antennas that may be in close proximity with each other that can interfere. So there's some serious coexistence issues there as well for desensitizing nearby antennas. They can lead to reduced dynamic range, loss of communication links, reduction of sensing qualities as well. And then the second point is also very important, and that is that if you have unwanted emissions, it can make you detectable in certain ways. So there can be a certain signature that your device has or your type of hardware has that can make you pretty detectable for hostile sensors. So characterizing unwanted emissions is becoming more and more important. So we're seeing that integrated antenna systems are now covering more bandwidth or multi-band operations or even multifunctional operations where we have sensing and communications integrated. We're also seeing more high power applications, and everything is in more close proximity to other wireless systems and getting more tightly integrated. So there's just more and more happening in that RF spectrum, making characterization of these emissions more and more important for both compliance, performance, and safety. So just to list a couple of use cases where it happens or what the effect is. So of course, in communications, we're seeing a reduction of signal quality or even a loss of link. If we're getting too much noise in our band or too much nonlinearities. Also, we do have an output power, so we can have some coexistence issues with, for example, very sensitive sensors that are placed in close proximity to it. Think of radar, reduced detection range. You could also use it to fingerprint a certain type of radar. Then there's also passive sensing, where of course we can desensitize a receiver by having too much emissions close to it, but it can also fool the sensor a little bit, just as it can fool a radar, that you have location errors or range Doppler errors, that latter in the case of a radar, of course. Then in SATCOM, there's also something really important where we need to have a very large dynamic range, since we have to cover such a large distance with our link. So anything that interferes with that or anything that blocks that level of dynamic range, such as other emissions, is going to be a problem. And especially an issue also in SATCOM is interference with radio astronomy. That's, by the way, also something we've seen with radars that are nearby. There's been radio astronomy sites such as the one in Alma in Chile, which really had an issue with a nearby radar. And again, any emission can be used as a signature exploit. So those are things to really take into account when characterizing unwanted emissions. Now, of course, you can use characterization to mitigate it by then applying, for example, filters, digital pre-distortion, or by increasing the isolation between your antennas or different equipment. So currently, there is a couple of ways to test radiated emissions, but really all of them depend on looking at one direction at a time in an anechoic chamber. So of course, an anechoic chamber is a radio silent environment, which is really good at isolating the effects from different angles. So it's really helpful to test things like radiation patterns for antennas, or to really look at what is happening at what direction. So we're looking at a single position. We are having an equipment under test or a device under test that is moving around, and a receiver or sometimes transmitter as well for immunity is looking at it angle by angle or position by position. Because of the time and because of just the nature of how that works, typically only a limited subset of angles is measured. And in some cases, even only single directions are measured. And now I will tell you a little bit about why that is problematic and why that is becoming problematic, especially at higher frequencies and for depths with more antennas. And it really has to do with basically the radiation pattern of our emissions. So to what direction are our emissions actually radiating to? So if we're looking at some measured radiation patterns, or if you look at models of what it actually looks like, we see two things. We see, first of all, that the beams get much narrower over frequency, so they get a lot more directive, but also just the whole pattern looks a lot more random. So there's two sources here given, so one by NIST and also one by FOI, this is the Swedish Defense Agency, where we see here, for example, in the result at 0.5 gigahertz, that there is variation. This was a dB scale, by the way. There is variation, but still, let's say you are sampling every 5 degrees, you're still good, and you would still pretty much capture this result. You would need to do a lot of measurements per those 5 degrees, but you'll still be able to capture this behavior. But when we're at 4 degrees, you can already see that 5 degrees is probably not enough, just because you could get in a null, or you could get in a peak, and you could miss a very important peak, for example, that adds to the total radiation. Here's also some results acquired by NIST, where you see it in linear scale and where you see really large differences between different angles. So that's really an issue, especially with unwanted emitters. Then you really get the splash type of pattern. But there's also an issue when we're talking about, in the EMC world, we would call them intentional radiators, or in the antenna world, you would just call them antennas, and you would just call this the pattern of the carrier, where you can see, of course, a similar result. So here we have that dimension, a maximum device under test dimension of about 0.5 meter, or approximately a little over 1.5 feet, where we can see that at 2 gigahertz, the pattern is a little less directive. And at 20 gigahertz, of course, we will have more antenna elements there. We will get a much higher directivity. So for antenna testing, this is challenging because, again, we need to be very precise with our placement of our reference antennas. But it's not only in the carrier frequency where we start to see this effect. And this is something that is very often overlooked. It's also in the unwanted emissions of those antennas where we are seeing these effects. So I have two examples here. One is given on the left. So this was a simulation of a 16-element phased array. This is linear, so we're just looking in one cut here, where we can see the pattern of the carrier frequency. And then we assumed here the harmonic to be lower in magnitude. But if you see how the harmonic frequency adds up in phase in the array, you can see that it goes into a completely different direction. So that's given here in red. So what that means is that if you're looking at the full spectrum only in the direction of the main beam, you are missing quite a lot of information, and you are missing the information of the harmonics. And it's not only the harmonic where this happens, it's also all of the nonlinearities of your array where this starts to happen. So that's where the picture on the right comes in, where we see on the y-axis at the level of gain and basically the adjacent channel leakage ratio or power ratio. And on the x-axis, we see the angles. So this was also a 2D cut. In blue, we see the gain of the system normalized. But what we are seeing here in red is the ratio of the ACPR. And you can see that per angle that varies quite a lot. So it really depends on where you place your antenna, what level of out-of-band emissions you're actually going to measure. And here you can see that the difference is huge. We're looking here at pretty much 40 dB of difference in out-of-band emissions between the different angles. And another way to visualize this is given here. So that's from that same paper, where we're also seeing that from the different subarrays that the nonlinearity is different. So the nonlinearity of subarray 1 is going in one direction, and the nonlinearity of subarray 2 is going into a different direction. So again, it's not just, low frequency EMC effects. It's also at high frequencies, we're seeing nonlinearities that are also quantified as unwanted emissions. So then if we would do a certain sampling, then we will see quite different results. So now I'm talking again about one of the results of the high directivity antenna, where we are trying to find a spur, and we're using different step sizes to do so. So again, let me just step back to one of those results. So one of those plots, if we're sampling this with 30 degrees at the time, or if we're sampling this at 1 degree at the time, we are really getting a different result. So again, here is a result where we're looking at 0.2 gigahertz. So that is a radiation pattern that is much more isotropic, where we're basically seeing the deviation of the actual radiated power that the device is radiating versus what we are measuring when we take a certain step size. So here you can see if we are taking a step size of 30 degrees, and here is basically the cumulative distribution. So this tells us what is the chance of getting a certain overestimation or underestimation. Here we are seeing that we are getting an underestimation of maximum about 0.1 dB if we're taking step sizes of 30 degrees. So that's fine. That's something that we can totally accept. However, if we go to higher frequencies, that's already a lot higher. So if we're taking step size of 30 degrees, there are cases where we're really getting many dBs of error. So just look at the difference in x-axis here. Then if we're going to 20 gigahertz, that difference really becomes huge. That even at 2.5 degree step size, we are seeing that 50% of the time we are getting already a few dB of error. So that's up to you on how much error you're willing to take and to accept. But I just want to make you aware that the higher we go up in frequency, the finer you need to sample, also for unwanted emissions. And that is maybe not something that is entirely doable, especially in anechoic chambers, where it takes a long time to sample that full sphere and to get all of those results. Especially when you don't know at what frequencies they occur or at what direction they occur. You could, in theory, do endless spherical scans for all frequencies, but that just takes a really long time. So again, a limitation of anechoic chambers is that it can be hard to capture an emission that is very directive, because you may miss certain angles that go around your equipment under test. But also when you're looking at high frequencies or large equipment under test, you really need to have a very fine spatial resolution. You're also likely to miss certain emissions that are time varying, because if something only happens at certain times and you just skipped over it, you also may miss it. And then the last point, which may also be relevant for mostly high power applications, is that your device under test or your equipment under test may not be able to remain in an on state for that amount of time to be able to capture it and measure it in an anechoic chamber. So those are some issues there. So it would be really helpful if there's a solution that immediately looks at all directions at the same time. And that also is not so dependent on like time variant or spatially variant effects. Like if we could see immediately get an integrator over all space that does that measurement really quick, that would be really helpful for this application and would remove a lot of the downsides or a lot of the issues that I've just explained to you. And one of those solutions is a reverberation chamber. So reverberation chamber does not get you the pattern, but it does get you everything related to overall radiated or received power. So here on the slide, you can see the inside of a reverberation chamber. So it is the dual of an anechoic chamber, where instead of the walls absorbing all of the information, here the walls reflect everything. And instead of a reference antenna or a receive antenna scanning around an emitter and then integrating over all of those fields, here we fix that reference antenna, but we change the electromagnetic environment. It's really easy how we do that. We change the electromagnetic environment by moving these mode stirring mechanisms. So these spindles that you see here, the vertical and the horizontal one, they just spin around and we change the environment. And again, it's really the equivalent as scanning around the device and then integrating over all of those fields. So also a chamber like this is often called an integrating sphere, and that works both in for transmitting metrics as well as receive metrics. So there's also people using these chambers for immunity or just receive quality testing. And just to show you a little bit what that setup looks like, here there's, for example, a radar that we're testing, and then there is just one receive antenna. This was an open-ended waveguide on the side. And by moving those stirrers around, always something will happen, will arrive at that receiver antenna, and the process works by averaging. So the longer we test, the more we average, and the more accurate we can get that result. So the reverb acts as an integrator of power transmitted in all directions, which is helpful. So nothing is hidden, no spur is hidden, or no nonlinearity is hidden. Doesn't matter what direction it goes to, you will be always able to find it and to see it. What's also helpful is that no mechanical scanning is needed and no alignment is needed. So we can just place the device inside. We don't really care about where's the phase center or what the device looks like. Because we change the environment, it really doesn't matter where we've placed the antenna. So it's really easy to set up, and no emission remains hidden. Of course, the trade-off is that you don't know exactly where that emission comes from in terms of direction, but you will know if it's there and what is the absolute level of the radiated power of that emission. So reverbs are really great for power-based metrics. Again, these are things that the anechoic is not so good at, so they're both really complementary. So if we're looking at things like total radiated power or measuring a power spectral density, whether we care about in or out of band emissions, or whether we care about a signal, or whether we care about noise, we can do that test really fast. So here you see a couple of results in terms of time and also level of uncertainty. You can test antenna efficiency really well, or power added efficiency, or anything that is a ratio that also relate to absolute powers. Noise figure is something you can do too in this chamber. And then, of course, what I'm going to talk about today mainly is spurious emissions, harmonics, oscillations, anything that is unwanted in your spectrum. And there you can see that, yeah, of course, depending on what bandwidth we're testing, if we're testing a huge bandwidth, or what level they are at, the uncertainty may be lower or higher, but these are just some typical values that you would see for a measurement. So there are smaller reverberation chambers. Ours is pretty small. You can see it here with a person in front of it. It always works with some equipment next to it. So some RF detection system besides it that captures the signal. And then there's algorithms added to reverberation chambers that basically subtract all of the losses in the chamber such that you can really get the total radiated power of that spur. So the absolute power level. This chamber, this one specifically works from 5 to 170 gigahertz. And you may wonder, like, what dictates the size and stuff like that, because in anechoic chambers, we really know this thing called far field distance. So far field distance is really not a thing in these chambers. It's not a concept that belongs to reverbs, because we don't need to scan a flat face front. We're diffusing everything immediately. So of course, we cannot be in the reactive near field of the device under test, because that will change the impedance and therefore the behavior of the device. However, we can in fact be in the radiative near field and still be good. Antennex is making larger chambers as well. And if you already have a reverb and you would like to try out some of the algorithms that I'm going to show you in a little bit, our algorithms also work, and our software works on many third-party chambers as well. So just wanted to mention that. Then also, if you go to a larger chamber, you'll be also able to go lower in frequency, because it's really based on how many modes fit inside of the chamber. So something that I already explained was that sort of we do this spatial integration. So we don't really miss anything that happens over space, but we can also do this in terms of time. So let's say we have something that only pops up sometimes. We'll be able to capture that as well if we use our chamber with an oscilloscope. So here you see we've done it for a radar. Just so you know, the results that we're seeing here do not correspond with the radar that's on the photo. But here we were testing a pulsed radar with a scope, so we could really get that pulsing behavior over time. So this was a wanted emission. This was just the operation of the radar in pulsed mode. where the RF was 60 gigahertz, and mixed it down to IF, and that's where we measured it. So that's also what you see here on the picture: chamber, mixer, and then oscilloscope. But similar techniques can also be used for unwanted emissions that are very time dependent. So let's say you're using a pulsed radar, and only in certain points you see a spur popping up. That's something you'll be able to check out in this chamber. So yeah, just to summarize a little bit about that. So a reverberation chamber is, by the nature of it, less sensitive to spatial variations. So it's not very sensitive to the directivity of your device, which gets quite unpredictable at high frequencies. But it's also not that sensitive to anything varying over time if you use the right instrument with it. However, what you measure at the measurand is different. So you test a different metric. So you're testing total radiated power over the space. That can be per frequency, or that can be integrated over a couple of frequencies in a power spectral density plot, for example. But it's not exactly the same as E-field strength, because in E-field strength, that is really defined as the strength of the field at a certain point in space. So often we're looking at total radiated power times the directivity that we are using, and then also typically defined at a certain distance. That's what we're seeing in a lot of standards, where we're just saying, I'll measure it at this specific distance. So they are related, but they're not exactly the same. However, TRP is quite helpful to use because we can always make sort of a model of what type of directivities we expect. But in the anechoic chamber, if you only measure a single point, you miss a lot. But in the reverb, if you measure TRP, you'll always know whether or not something is there. So what we're seeing now is that because of some of the challenges that are happening in testing E-field strength, that we also see standards moving towards accepting TRP more. Because if you test TRP, you'll get more of like a real world compliance instead of just having a little bit of luck whether or not you pass the test. Especially for critical applications, that's something that you probably don't really want. So what we typically say, if you do care about the direction of radiation, is to have a two-step approach, where you first do a TRP measurement in the reverberation chamber. You can do this over larger bandwidths, so you can really see exactly where spurs are happening and where they do occur. However, if you then really care about exactly what direction it's going to, then you can go to the anechoic chamber and you will know exactly where to look for it. So that is going to, in the end, save you quite a lot of time, so you're not scanning for things that are not there in the anechoic. So then a couple of examples of measurements that we did in the reverb, so you have sort of an idea of what the results look like that you're getting from them. So I think I have 4 or 5 different results. So here we did identification of emissions at very specific frequencies in continuous wave mode. So we just had a test tone that was sent out by an autonomous emitter. And in this case, that was an E-band 64 element phased array. So this was operating around 60 gigahertz. And we normalized the results for confidentiality. However, if we look at this result, we of course see the carrier continuous wave tone here normalized to 0 hertz, but we see quite a lot of other emissions as well in the spectrum. So we are seeing a low leakage. We are seeing also a very clear presence of clock spurs at every 50 hertz. And to get you this result is really in the order of seconds. So you could try it out for a lot of different channels and see if things vary for different channels. So that is this is one example of what was captured in the reverb. And again, no alignment was needed. We just placed the array inside, turned on the test, and immediately got this result. Another result that I want to show you is something we did a little bit as a joke a couple of weeks ago, but we placed a small consumer drone in the reverb, where the drone had a 5.8 gigahertz analog video transmitter. Again, this drone did not have an RF input or a power input or anything. It was just an autonomous emitter that we just placed inside, closed the door, and ran the test. So configuring the spectrum analyzer in the chamber was less than 5 minutes. And really setup and testing time, both together, was less than 1 minute. It was placing it inside, closing the door, and that's it. And then we got the result here on the right-hand side. So we can see very clearly the harmonics of 2 and 3 times the 5.8 gigahertz. But there's also some other things happening here in the spectrum that, yeah, we don't know yet where they're coming from, but at least we know they're there. So this might be important for several issues, for like compliance, but also detectability. This result was uncalibrated, but it's good to know that if we take a couple more minutes to calibrate the transfer function of the chamber, which we can do very precisely, we'll be able to know this result exactly. At the frequency where we tested, the loss of the chamber is about 20 dB. So this harmonic was in the order of minus 40 dBm. I think that was averaged over 1 megahertz. Then another application where we're also really looking more towards performance of devices. Here we had a 100 gigahertz antenna in package. This was an antenna in package from NXP. So you can see a photo of it here. So it's like the size of a small stamp, where we were first testing it in an anechoic chamber. This was already a couple of years ago, by the way. And we were doing an IF in RF out test, and we were seeing very clearly that there was a very strong variation in the measured signal, in the output signal of the RF, for not a reason that we could immediately identify. So we could not immediately diagnose it. We saw variations in DC current and the RF amplitude, so we knew that some things were up, but we were just not sure. And this is really where the reverb came in, because I believe this problem remained for a couple of weeks even, because we were not sure if it was the test setup, if it was the device under test, or if it was the instrument. So there was quite a lot of debugging already that we did, but just the anechoic chamber didn't give us enough information to find what was up. So that's when we placed it in the reverb and really saw immediately what was going on. So when we placed it inside, we identified the issue within a day, where in the end it was found that some IF was leaking into the LO port, and there were some issues that related to that. So what we were seeing is when we were varying the power of the LO, you could see immediately that the power did not scale with the settings that we are seeing here. So here you can see LO 0 dB to LO minus 7 dB. So it didn't scale in the same way with the same ratio, but also we saw jumping to different frequencies when that happens. So there were some issues there that were, thanks to these measurements, resolved afterwards. So again, it's not necessarily an harmonic or an unwanted emission somewhere else. It can also be a small performance issue that is shown in the way of an unwanted emission at a different frequency. Then one of the last results here is also that we can do identification of in and outband distortions at specific frequencies under wideband conditions. So what we did here is we had an antenna with a power amplifier. You can see on the x-axis frequency, on the y-axis we see the normalized power, but just so you know, we can also measure it absolute. This was done with a vector signal generator and analyzer, where we upped the power a little bit, and what we saw is that there were immediately these sidebands occurring. So we saw that the adjacent channel leakage ratio was getting higher, but we're also seeing that in-band distortion here as well was getting higher. So you can get something like noise power ratio from here too. And this was because we left a gap in the middle of the multitone signal with the VSG. Now, some things that we are working on is that we are working on algorithms to isolate noise from nonlinear distortions and a signal, such that we have in-band and out-of-band distortions isolated. Here you can see a result that was also captured in our chamber. We're also working on adding functionalities such as ERP or the E-field strength at a specific direction, and we're also working on larger chambers. What I just very briefly want to show you is 3 other tests that we can do in this chamber that may be relevant to you in the audience here, and then I'll open the floor to questions. The first one is noise figure. We can use this chamber as a wireless noise source to do noise figure measurements, where we can do with a cold source method and one single setup with a PNAX, a gain measurement and a noise figure measurement, where the test time is about 1 minute for 1 gigahertz of bandwidth. And again, no alignment needed of the device under test. You can place it anywhere in the chamber. You'll get these slides afterwards, by the way, so I'll just skip through these a little fast. There's also an option for antenna efficiency. So you can get total efficiency, which includes the antenna mismatch, radiation efficiency, which excludes the antenna mismatch. So you also get the antenna mismatch for reciprocal antennas that are passive. But we can also do active antennas. So think of gain. Again, no alignment needed. Here are some typical test times. For a passive antenna, we can just do it with a one-port measurement, and the calibration of the chamber is done at the same time as the test. So you can see what the efficiency of your antenna is with different radomes, for conformal antennas, if you have a different packaging. So that can be helpful for those for applications where you really want to optimize dynamic range, or where you use, for example, high powers and a lower antenna efficiency can lead to heating problems. Something else that you can do in the chamber that I already showed a little bit before is to test radar signals. So there can be FMCW signals, pulsed radars, or different waveforms can also be tested. Specifically with this type of testing, we have so much bandwidth that we can use to calculate things such as total radiated power. That means that we can do the test really quickly. So we're really below 1 second test time. So just to get to a conclusion, we see that equipments under tests in aerospace and defense are changing. We're seeing more bandwidth, more power, and definitely a lot more antennas at higher frequencies. So you just have a higher chance of getting more unwanted emissions. The characterization of those unwanted emissions is important for compliance, performance, and also safety. When we go to higher frequencies, it becomes much more difficult to characterize them because the direction of radiation can be unpredictable, and a reverb chamber can be a nice solution for this because no information remains hidden, making the test more accurate and faster. Should you be interested in trying that, our company Antennex makes those types of systems. We make reverberation chambers. We're based in the Netherlands, where our headquarters is in Europe, but we also have a support center in LA, where Paul is helping us out. We have a long history in doing anechoic chambers, and we really got here doing reverbs from seeing the issues ourselves of having anechoic chambers. So we're a company run by experienced antenna and RF metrologists. That's where these techniques also come from. We're now a team of 15 people. And if you're interested in trying out Antennex in your lab, just know that it's compatible with several RF instrument brands from Keysight, Rode, NI, and Tech. There's options for rent to buy, purchase. We also do demos on site and trials. And there's options for software only deals for existing chambers and also for consultancy. And again, in the US, Electrorent is our exclusive distributor. So here I would like to give the word to Paul for a final closing.
Oh, well, thank you, Anouk. This was a great presentation, and I thank you for the wealth of knowledge here that you shared with us in regards to these type of spurious emissions that could be done over the air with this chamber. As you know, as Anouk said, Electrorent is the exclusive US provider. Feel free to reach out to us, contact your local Electrorent account manager, or reach out to us at electrorent.com. Our contact info is here, as you see, with our phone number, or you can also reach out to us via our LinkedIn page or social media, or feel free to reach out to me directly. Thank you, everyone.
Great. Thank you, Paul. If there are any questions, you can just place them in the chat and I'll be happy to answer them. There's a question about measuring TRP in the millimeter wave band. Is there a research with comprehensive comparison of the two methods, probe scanning in anechoic environment versus reverberation chamber, expanded uncertainty with the same measuring receiver, measurement time, setup construction, and maintenance cost? I could get you one of those comparisons if you're interested in that. So I think I do have your contact here. In terms of comparisons with scanning, I just gave you one of the examples of how far the delta can get in an anechoic chamber, depending on the scanning the resolution that you are using, which is inherently not an error that you see in the reverb. Also things as antenna alignment or long cables or calibration or stuff like that, or even calibration of free space path loss is something that you don't see in the reverb. The sources of uncertainty that you do see in the reverb is estimation of the transfer function of the reverb, where again, what I just gave you, the uncertainty, again, depending on your settings, but in typical settings, we had 0.2 dB of 2 sigma. Added to that is, of course, uncertainties due to the instrument that you use next to it. So whether that's a VNA or a spectrum analyzer, that's going to be added onto that. In terms of measurement time, the differences are really extremely big. So we are really talking many orders of magnitude here. So if we want to do a TRP with a single probe anechoic chamber with a fine resolution, it could be really hours that you're measuring, but at least half an hour, I would say. In the reverb, you're getting the same quality or probably even higher quality in really a couple of seconds. So that is the difference that we're talking with here. And that's really just because the technology of a reverb is much better at integrating overall of the fields. Again, with the downside is that you don't get the pattern. Setup construction. So I'm just going to go by them one by one. Setup construction, also the same thing. My personal experience with the anechoic chamber is really that it can take a couple of hours to set up everything, to calibrate it. But in a reverb, you don't need to align it. So you can just place it inside, making the setup very, very quickly. No need for long cables, which also helps in your uncertainty budget. And maintenance cost is a lot lower too. Yeah, just because it is metal, there's not a lot of maintenance there. So it's not like the absorbers that are maybe degrading or that are slowly falling apart. Bandwidth is higher just because it is metal. So it's not really limited to a certain band, except that a certain amount of modes needs to fit in the chamber. So yeah, when it comes to TRP, there is really only benefits when it comes to a reverb compared to the anechoic chamber. Yeah, or mostly advantages, definitely. I hope that answers your question a little bit, and I can try to get a more like a table ready for you if you have a specific use case. Let me know if that answered your question or if you have a follow-up question. If there are other people that are having questions, just drop them in the chat and I can cover them here. Okay, there's another question that I think is being typed right now.
Could you kindly note standards moving from Eastern to TRP criteria?
Yes, I'm sorry. I read it the first time I read it as if I could let standards know, but yeah, I can tell you the standards. So I also have my CTO Teun on the call, who can maybe detail a little bit more about those specific standards and also the current developments that we are seeing in some EMC standards. So Teun, could you turn on your camera and microphone maybe?
Yes, I hope you can hear me well because I'm at an event and a conference. But to your question, yes, so there are some standards that are currently already being accepted. So one of the examples is actually the aerospace and defense standard, or the aerospace standard, sorry, RTCA DO 160, that actually allows for TRP. As a complementary standard to the E-field at a distance. And also in multimedia standard is currently being drafted. So that is actually more towards the consumer market, but also there you see the movement from E-field at a distance towards TRP, and the same in automotive. There is also a standard being drafted. So there is some traction happening there. We're slowly getting to, let's say, that both metrics are both being accepted.
Teun, is there a way you can drop the names of those standards in the chat just for reference?
Yeah, Yes, sure, I can do it.
Thanks a lot. All right. Are there maybe any other questions from the attendees? And I hope that answered your question if we drop them in the chat. There's also going to be, by the way, a blog post online about that pretty soon. I'm just looking to my colleague here real quick. When is that going to be?
I will post it later this week, and it tackles this question directly.
Okay, I hope you heard that. But there will be a blog post on our website just later this week. Let's see, I'm just going to give a little bit of time to see if other people are typing questions or if they want to know anything else. I'm calling in, by the way, from the Antennex lab, so you can see here in the back a couple of chambers. There's a couple in front of me and next to me as well. This is based in Eindhoven, the Netherlands, where the chambers are all locally produced. Great. Okay. Thank you for confirming that that the information was complete. I'm just going to wait a little bit until Toon drops those standards names in the chat, so we are sure that we get them.
Give me 1 more minute.
Yeah, sure. So that we don't drop off and close it before everybody has that information, so you can use it for your own reference. Also, if you like to stay up to date with Antennex, we post most of the latest information on our website. So we post like blog posts, use cases, updates and explanations about the technology. So we're adding quite a lot of new content these days. And it's also going to be added on LinkedIn. So if you're interested, just follow our LinkedIn post. We have a quarterly newsletter as well that you can subscribe to if you like. So we don't try to spam you with useless information. We really try to give you meaningful updates about the technology and about the functionalities of this new system. Any plans or thoughts on using VERCs as your chambers? That's a great question. So yeah, for the people that are not familiar with that, VERCs are vibrating intrinsic reverberation chambers. They're sort of metal-laced fabric. So instead of turning those spindles around, we just have a tent that we shake. So that's really helpful for larger, especially larger form factor antennas. So if you want to place like an entire ship or something in it, you may be able to do so. And I think also it was introduced for mostly military purposes. And they're also really great for things like TRP testing and metrics such as that. So definitely our software could be used with VERCs. We've done some research on them, but we don't sell VERCs ourselves. Limitations of VERCs are mainly in tests where you really need to get an accurate representation of the volume. So there is some calculations in those by using those chambers where you really need to know the volume. That's challenging in a VERC because the volume varies. So that's a level of uncertainty that gets added there that you don't have in classical reverbs. And something else as well is that you can see a lot of early time direct reflections from it. Just because everything is moving around it, you sometimes get errors from that as well. And for metrics such as noise figure, you also need to do a stepped stirring. So some measurements can be done continuously. Many TRP measurements can, and they're great for that. Certain stepped ones, then you really need a more predictable environment, which you get from the classical reverb. So no plans right now on using VERCs, but they're definitely awesome. And our software can be used for them if that's anything that ever interests the people on this call. I hope that answered your question, Alejandro. And then I see that Teun also added some information on where certain standards add conversion metrics and where certain standards are still working on that, basically. And Teun also gave his email address if you want to hear more information about specifically the automotive standard. Okay, and thank you for confirming that that your question is answered, Alejandro. All right, then let's just maybe let's see if more questions drop in the next minute or so. Otherwise, if no more questions drop in, then I'll let you get back to work. For the American attendees and for the Europeans, I will let you get back to having a nice night. So I'm also going to post my email address in the chat if there are any more questions for me as well, or if there's a
Same here.
specific request. And Paul will do the same if you're in the Americas and you have questions about trying out the system. Again, we do demos, trials, and to just lower the bar for you to try out this new technology and to validate. And we can also help you cross-correlate it with your existing anechoic chamber measurements. Also in terms of, not in terms of only absolute results, but also in terms of uncertainty, budget, and cost, and things like that. And thank you for the nice compliment, Taimi. Then I think no more questions are dropping in and we are ready to close off. I just want to say I really appreciate your time for the Americas to join in on your morning or like early afternoon, and also for the Europeans to join in this late. I'm not sure how many Asian attendees we have as well. Not sure. I didn't see any. Anyways, if you are, and I'm not mentioning you, thanks a lot for attending and listening to the presentation. And if you have any questions, feel free to reach out and just drop us a follow on LinkedIn if you're interested on staying up to date.
Great.
Great.
Well, thank you so much, Anouk and the Antennex team. Thank you all for attending today's webinar, and there'll be more to come. Thank you all.
Definitely. Okay. All right. Have a nice day, everybody.